Hello, welcome to the two-phase flow and heat transfer course. We are in the first lecture, Introduction to Two-Phase Flow. I am Dr. Arup Kumar Das. I will be selling you through this course. Along with me, I am having my teaching assistant Mr. Pramod Kumar. So, if necessary, you can contact both of us during this course. Okay, first I will be showing you the syllabus what we will be covering in this course. As you know that this course will be spanning 4 weeks and each week we are having 5 modules. So, what we have done, we have described or we have divided the syllabus into 20 lectures over here. So, in the first week we will be giving you brief introduction of the two-phase flow. We will be discussing about different flow regimes available in two-phase flow in the second module. In first week third module we will be discussing about the easiest model possible, which is called homogeneous model. Then we will be going for drift flux model where slip between the phases we will be considering, and finally at the end of this week we will be finding out that how separated flow can model two-phase flow over here. At the end of this week we will be getting one assignment, okay, mainly this assignment will be MCQ type. In the second week we will be discussing the several regimes separately. For example, we will be starting from dispersed flow, then we will be talking about slug flow, annular flow, and we will be also discussing about droplet, annular and stratified flow together in one lecture. At the end of this week we will be also understanding how to measure experimentally the void fraction. So, at the end of second week, just like the first week, we will be also having one assignment, okay, and in third week we will be starting with signal analysis. Mainly we will be doing here the measurement of void fraction, whatever data we have received. From there, by doing signal analysis we will be trying to understand the flow regimes. Apart from that, I will be showing you different numerical models also in this week. We will be starting with two fluid balance, population balance model. Then I will be showing you how to track the interface using volume of fluid, and we will be learning some advanced methodologies like lattice-Boltzmann smoothed particle hydrodynamics and molecular dynamics. Okay. So, at the end of third week we will be also getting one set of assignment, and in the last week we will be seeing some specific cases like boiling heat transfer. So, phase change, then we will be having just the reverse one, condensation, and towards the end of this lecture we will be having solid liquid flow and gas solid flow. Okay. And at the end of fourth week also we will be having a set of assignments, and finally it will be followed by one end semester examination. So, some suggested book, we are having some books as textbook. S.M. Ghassian, C.E. Brennan, Thom Collier and Wallis, these books you can follow if necessary. Some related journals where you will be finding out lectures of two-phase flow and innovations of two-phase flow is coming as published form. Now, quickly I will be coming to the outline of the first lecture. So, in this lecture we will be learning about what are the target areas of two-phase flow. Also we will be learning what are the daily life and industrial applications of two-phase flow, and towards the end of this lecture we will be learning about different terminologies to be used in the future course of two-phase flow and several useful notations for two-phase flow and heat transfer. So, to begin with, let us understand what are different phases possible in real world. We can find out solid phase, liquid phase as well as gaseous phase. We know that molecular structure of all these phases are not similar. In case of solid phase we are having closely packed, and in case of gaseous phase this is loosely packed, and liquid is somewhere in between. Now, if we are having association of two different substances of phases or two different components, we will be calling that one as two-phase flow. Now, breaking and making of time and space variant interface is the common feature of two-phase flow. Here I have shown you well separated flow. You can see a kerosene slug in water, blue colored thing is kerosene, and around we are having white colored fluid which is nothing but water. So, you can see the well and distinct interface of the kerosene slug over here. But on the other hand, in this figure I have shown you well dispersed flow of kerosene in water. So, lots of blue colored bubbles you can see in water flow. So, these are two different horizons, well separated flow and well dispersed flow. Now, due to these things we are having two different type of features over here. Here we have shown a schematic video of bubbly flow in a channel. So, you can find out existence of two phases over here. So, this is the gaseous phase and around we are having liquid phase. Apart from that, if you see the video once again, you will be finding out a well distinct interface you can see, which is a bigger in size and smaller bubbles are also passing. So, that means it is the occurrence of multi-scale. Side by side, definitely as the scales are different, we will be having different physics for this type of problem. Next, let us come to different domains of two phase flow. So, we are having single phases over here, gas, liquid and solid. So, if we are having occurrences where gas and liquid comes together, that is gas liquid two phase flow, gas and solid comes together, we are having gas solid two phase flow, and simultaneously if solid and liquid comes together, we will be having solid liquid two phase flow. There can be some sort of examples in real life and industry where all three phases comes together, and this we call as three phase flow. Let me give you some examples over here. This is another time I am running that video where you can find out gaseous air and liquid water in coexistence. So, this is a typical example of gas liquid two phase flow. Next, I will be showing you another one where you can find out liquid drop is situated on a solid surface and due to some electric field application it is changing its shape and size. So, you can find out this is typical example of liquid solid two phase flow. Another one, here I have shown gas and solid. So, you can see these are solid particles which is coming inside, and you can find out here we are having association between gas and solid. So, this is a typical example of gas and solid two phase flow. We are also having examples of three phase flow over here where you can see solid ice, liquid water and air in the vicinity. So, this is a typical example of three phase flow. Okay. Let us now see that based on heat transfer how two phase flow can be categorized. If there is no heat transfer associated, so you will be finding out adiabatic conditions. So, pipe will be having no phase change inside this, but if you are having phase change or allowed heat transfer, so we can have three different situations: boiling or condensation, melting and solidification, and finally sublimation and deposition. So, boiling and condensation is associated with gas liquid regimes, melting and solidification is associated with solid and liquid regime, and finally sublimation or deposition is associated with gas and solid regimes. So, here I have noted down some of the important applications of all these three regimes: boiling and condensation, melting and solidification, and finally sublimation and deposition. Next, let us see how two phase flow horizon is nowadays changing. So, if we talk about flow, always it comes in your mind that both the phases will be flowing simultaneously. So, here I have shown one video, you can see kerosene is flowing from left to right and water is also flowing from left to right. So, we are having well and defined interface in between these two. So, this actually we can call as two phase flow, but you can find out some examples where predominant motion of the primary phase is not there. Only by impinging the secondary phase the motion is being generated in the primary phase. So, this kind of situation actually also we are taking inside the horizon of two phase flow. So, it is not only about the flow, if the flow is being generated by the secondary phase, that also we can tackle inside the two phase flow horizon. Okay. Next, without knowing the applications or daily life examples, any subject we will not be studying. So, here what I have done, I have given you some ideas about the applications of two phase flow. So, you see these are different occurrences of two phase flow in nature, starting from water wave, gas liquid two phase flow, dews on leaves. So, this is once again gas liquid two phase flow. Here you can find out spitting cobra, a cobra is spitting. So, this is actually once again gas liquid two phase flow, geyser, waterfall. So, downstream of waterfall, geyser means we will be having hot bubbles bursting in the liquid surface, lots of droplets are being generated, as well as daily life rain we can see, all those are example of gas liquid two phase flow. Different occurrences in daily life, sweating, in our kitchen sink we can find out lots of bubbles are being entrapped in the kitchen sink. While you are emptying a bottle, we can find out gas liquid two phase flow over here. You are sprinkling in your garden, so this is also one example of gas liquid two phase flow. If you are mixing your tea with your sugar or milk, so you will be finding out lots of bubbles are actually being entrapped over here. So, this is one example of two phase flow. Also we are having another example where you can find out you are pouring water in a glass, so lots of bubbles are being entrapped. So this is also example of two-phase flow. Some other examples in your daily life, in your toilet sink, whenever you are taking bath, in the soap foam, you are drinking a buttermilk, so whenever buttermilk is being stirred for mixing, two-phase flow is being generated, lots of bubbles. In shower, aquarium pump, lots of bubbles are being generated, very classy looking things. We are also having some refreshment drink, at the top of the drink you can find out a foam, and at the bottom you can find out lots of bubbles. So this is another example of two-phase flow. Also in the shaving foam, which is typical example of two-phase flow once again. Few other examples we can see over here. So whenever you are swimming in different sports activities, water polo, windsurfing, underwater swimming and rafting, all these are examples of gas liquid two-phase flow. And in case of ice skating, you can find out ice flakes in the form of solid is coming into picture in case of air. So this is actually solid gas two-phase flow. Next, few other examples of two-phase flow. Whenever your car is splashing in water, so you can find out lots of droplets are being generated. While helicopter is landing, so you can find out lots of gas solid flow is over here. Spider wave, this is once again solid liquid two-phase flow, so you can find lots of droplets on the solid spider web. In case of dripping, in hospital we go for dripping, so you can find out nice droplets are being created over here, once again two-phase flow. Sandstorm, natural phenomena, gas solid two-phase flow over here. If you go for fountain, this is a famous fountain in Geneva, so you can find out lots of droplets are being created in the form of a mist, once again two-phase flow. Cappuccino, lots of nice figures we have seen in case of cappuccino, so you can find out here also we are having typical example of two-phase flow, liquid liquid two-phase flow. Few examples over here for industrial applications, because without industrial application we do not feel that subject is becoming interesting. So few examples of industrial applications. In case of pneumatic conveying, so you will be finding out gas solid two-phase flow is over here. In case of cyclone separator, once again you will be finding out that using this cyclone separator we can separate the solid from the gas. So this is once again example of gas solid two-phase flow. Airlift pump and geyser pump, these are being applied for pumping some liquid using gas. So here using bubbles we pump the liquid, and here using a Taylor bubble or slug bubble we pump the liquid from lower position to higher position. So these are typical examples of gas liquid two-phase flow. In our car we can see fuel injector, definitely that is atomizing the liquid fuel into droplet. So typical example of gas liquid two-phase flow. In machining, water jet machining, you can find out a fast moving water jet is over here, which is actually cutting the metallic sheet. So this is once again typical example of gas liquid two-phase flow. Here we have shown example of slurry transport pipeline. So you can find out here also we are having solid liquid two-phase flow into coexistence. Few other examples over here. So these examples are associated with phase change. So you can find out in boiler tube, so liquid is being converted to gas. We are also having similar example in condenser where gas is converting into liquid. So you can find out these things in our power plant. Here I have shown you oil exploration. You will be finding out lots of liquid liquid two-phase flow in oil exploration plant. Once again example of industrial two-phase flow. Falling film evaporator, cooling towers, these are also part of your power plant, but everywhere we are having examples of two-phase flow. Evaporative heat exchanger, this is also typical example of heat exchanger where using heat we are getting the change of phase and we are having two-phase flow. Next, let us try to understand what are the different notations of two-phase flow. So first I will be showing you this figure. You can find out this is actually a cross section of a tube, and here with this liquid color, blue color, we have shown you one phase, and with this white color you have shown you other phase. Let us consider that this blue color thing is liquid and this white color fluid is actually gas. So fluid is being noted by F and gas is being noted by G. So the area if you try to find out which is occupied by liquid, we are calling that as AF, and the gas is occupying area which is nothing but AG. So from the area average we can write down A is equals to AF plus AG, right. So from this figure you can find out this relation is valid, A equals to AF plus AG. Now let us try to understand what are the different notation based on this figure. we will be using in two-phase flow. First one, we will be going for void fraction. We usually write down void fraction as alpha. The definition of void fraction alpha is area occupied by the gas to the area occupied by the pipeline. So, you see the whole pipeline is having area A and the gas is occupying this much area. So, the ratio between Ag and A is called as void fraction. So, obviously using this relationship along with this one, we can find out 1 minus alpha will be AF by A. Okay. So, if you add these two, then you will be getting this equation once again back, right. So, after the void fraction, which is very important parameter in case of two-phase flow, let us see what is mass flow rate. So, we are having next term as mass flow rate. Usually we write down mass flow rate in two-phase flow as W. So, Wg is for the gaseous mass flow rate and Wf is for the liquid mass flow rate. Now, as we know that continuity equation is valid from fluid mechanics we know. So, we can write down total mass flow rate W is equals to Wf plus Wg. Now, if we try to write down individually this mass flow rates, so we can write down from continuity equation once again Wg gaseous mass flow rate is equals to rho g, Ug and Ag. So, Ug and Ag is the gaseous volume flow rate multiplied by rho g is the mass flow rate or for the gas. Similarly, we can write down for the liquid Wf is equals to rho f, Uf and Af. Right. So, after the mass flow rate, let us try to see what is volumetric flow rate. So, volumetric flow rate usually we go for Q. So, we write down Qg and Qf. Okay. So, let us see first what happens for the volumetric flow rate. So, Qg we can write down obviously Ug into Ag. Here density will not be coming into picture like your mass flow rate over here. So, Qg we can write down the volumetric flux is actually Ug into Ag. Now, if you try to club these two equation, you will be finding out that Ug into Ag from here can be written as Wg by Ag. So, we can write down Qg is equals to Wg by rho g. Right. In a similar fashion, we can write down Qf is equals to Uf into Af, volumetric flow rate for your liquid, and we can write down Uf into Af is equals to Wf by rho f from this equation. So, you can find out Qf turns out to be Wf by rho f. We can write down by adding these two, Q equals to total flow rate, total volumetric flow rate is equals to Qf plus Qg, right. So, after the flow rates, let us try to see how the flux is coming out. First, we will be going for mass flux. Sometime we call this as mass velocity also. We denote this as g. So, g is actually for the total mass velocity including both the phases. We can write down g is equals to W by A, right. Now, Gj, so this is for gaseous phase mass velocity is Wg by A. So, whenever you are having Wg by A as the gaseous phase mass flow rate, similarly we can write down for the liquid flow rate Wf by A is equals to Gf. So, adding these two, you can write down total mass velocity G is actually Gg plus Gf, right. Let us try to see then the volumetric flux. For in case of volumetric flux, we will be writing that one as small j. So, small j is actually total volumetric flow divided by the area. So, this is Q by A. So, sometime we call this as superficial velocity also, right. For gaseous phase, if we try to find out, Jg will be equal to Qg by A, corresponding counterpart for the gaseous phase, and in the liquid phase we can write down Jf is equals to Qf by A. Now, if you add these two, then you will be getting at the top Qg by Qf, and at the bottom you will be having Ag by Af from these two, and along with the previous slides equations, A equals to Af plus Ag and Q equals to Qf plus Qg, you can find out J becomes Jg plus Jf, right. So, after the flux, let us try to find out few more quantities like mass quality or X. So, X is already known to us from our thermodynamics knowledge. Let us recapitulate that one. So, X we know nothing but mass for the gaseous phase divided by the whole mass. So, this is Wg by W. Definitely 1 minus X will be Wf by W, and we know from thermodynamics that X can be written as 1 minus If, where I is the enthalpy divided by Ifg, right. In a similar fashion, we can go for volumetric quality. So, this is mass quality. Next, we are going to define the volumetric quality. Usually, we write down volumetric quality as beta. So, beta is actually Qg by Q, right. So, this is actually gaseous phase volumetric flow divided by the total volumetric flow. Ratio between these two is called as volumetric quality beta. In a similar fashion, 1 minus beta can be written as QF by Q. Now, as it is two phase flow, so there will be something called relative velocity. Relative velocity means the velocity between the gaseous phase and the liquid phase. So, what we have done here, we have defined relative velocity as UGF. So, UGF definitely it will be the subtraction between UG gaseous phase velocity minus of UF, and simultaneously we can write down UFG, which is just the opposite UF minus UG, right. So, you can find out over here that UGF is equals to minus of UFG, because these expressions are actually having opposite signs to each other, right. Now, after this relative velocity, let us try to find out what is drift velocity. So, what is drift actually? One phase, how much it is lagging from the overall phase velocities. So, that is actually drift. So, already we have seen the overall phase velocity we can write down, or superficial velocity we can write down as j. So, individual phase how much it is lagging we can find out by the subtraction of their velocity and the superficial velocity. So, you see UF minus j is the velocity by which the liquid phase is lagging from the overall flow. So, you can write down this one as drift velocity for the liquid UFJ is equals to UF minus j, right. In the same fashion, we can write down for gas. So, UGJ is equals to UG minus j, how much the gas is actually drifting from the overall flow. Next, let us define another term called drift flux. So, drift flux is giving you some sort of idea that how much liquid is actually drifting from the gas. Earlier, whenever we have described drift velocity, that was how much it was drifting from the overall velocity. So, here overall superficial velocity, here we are finding out how much the liquid is drifting from the gas velocity. So, we will be defining JGF is equals to alpha into UG minus UJ. So, you see UG minus J, it was UGJ. So, I can write down JGF is equals to alpha into UGJ. In the same manner, just opposite version of this, JFG can be written as 1 minus alpha into UF minus J. Now, already we have seen UF minus J is UFJ. So, we can write down 1 minus alpha into UFJ is equals to JFG. Next, here let us see some useful relationships for two phase flow. So, first let us try to find out the liquid velocity UF. So, UF from the continuity equation we can write down, that is nothing but mass flow rate divided by density into area. So, here we have written down Wf divided by rho f into AF. Here you see Wf into rho f into AF, this can be also written as Wf by rho f is actually Qf. So, we can write down Uf is equals to Qf by AF, right. On the other hand, you see already we have shown in the previous slide that JGF is equals to alpha into UJG. So, what we can do here, this AF and QF, this we can write down in terms of this. How? Let us try to see. Let us try to see how we can write down this one. So, first let us see UF is actually we can write down this is WF by rho f into AF. Okay. So, here you see we can write down this one as W into 1 minus x and then rho f. In place of AF we can write down A into 1 minus alpha, right. These two definitions already we have shown that WF will be W into 1 minus x, similarly AF will be A into 1 minus alpha. Now, here you see W by A we can write down G, which already we have shown. So, this turns out to be G into 1 minus x into rho f into 1 minus alpha, right, which I have shown you over here. You see G into 1 minus x divided by 1 minus alpha into rho f. Okay. In a similar fashion, the counterpart can also be proved. So, UG is actually Wg divided by rho g into Ag. So, you can write down this one is W into x. So, Wg I am writing W into x, rho g, and Ag we can write down alpha into A. So, you can write down this is actually Gx by rho g into alpha. So, second equation I have shown you over here, Ug is equals to Gx by alpha into rho g. Now, if you make the ratio between UF and UG from these two equations, so you will be finding out G and G will be cancelling out, and finally this equation you will be getting x by 1 minus x rho f by rho g into 1 minus alpha by alpha, right. So, next let us try to see that how Jg can be written in terms of alpha and beta. So, let us see next how Jg can be written in terms of alpha and beta. We will be starting from Jg, we can write down in the form of Ug into alpha, right. So, how alpha is coming over here? Alpha is nothing but Ug into Ag by A. So, you see over here Ug into Ag, that can be written as Qg divided by A, which is the definition of your Jg. In a similar fashion, we can prove the terminologies involving Jf. So, Jf will be Uf into 1 minus alpha. So, you can find out Uf and 1 minus alpha can be written as Af by A. So, you can find out this is Qf by A, which is nothing but the definition of Jf. So, after proving all this, let us try to see two important relationships. Over here you see we can write down Jfg is equals to alpha into Jf minus of 1 minus alpha into Jg. Let us try to prove this. So, we will be starting from this equation, Jfg is equals to 1 minus alpha into Uf minus J. So, Jfg is equals to 1 minus alpha into Uf minus J, right. So, I can write down over here 1 minus alpha into Uf and then 1 minus alpha into J can be written as Jg plus Jf, right. So, 1 minus alpha into Uf, that will be alpha into Jf. This I have shown you over here, okay. So, this I have shown you over here. So, finally, you will be getting minus 1 minus alpha into Jg plus Jf. So, ultimately if you take several terms common, then you will be getting this final equation Jgf is equal Jfg is equals to alpha into Jf minus of 1 minus alpha into Jg. So, this I get over here alpha into Jf minus of 1 minus alpha into Jg, right. In a similar fashion, we can write down for Jgf, which will be nothing but 1 minus alpha into Jg minus of alpha into Jf. So, from these two equations you can write down that Jgf is equals to minus of Jfg. On the other hand, if you write down Jgf in the form of Ugf, you will be finding out the coefficient becomes alpha into 1 minus alpha. This can be proved once again from here. So, I will be starting with Jgf. So, Jgf you can see we can write down from here Jgf is actually 1 minus alpha into Jg minus of alpha into Jf. So, 1 minus alpha into Jg minus of alpha into Jf, okay. So, from here if you try to replace this Jg and Jf in terms of your Ug and Uf, so you will be getting 1 minus alpha into Ug and alpha into 1 minus alpha into Uf. So, ultimately you get 1 minus alpha into Ugf, okay. So, this is the final equation we have written down over here, which will be very important for two phase flow. right. Next, let us summarize this lecture. So, what we have done, we have studied different applications of two phase flow over here, discussed possible configurations in industrial examples, and at the end we have summarized different notations, basic relations and useful correlations over here in two phase flow. Let us try to find out how we have gone through in this lecture. So, some understanding we will be trying to test you. First question, which is the following is not an example of two phase flow: swimming, flow inside a pipe, cooling tower and boiling. So, the answer is flow inside a pipe. Definitely this is a single phase example. Recognize the correct one. We are having 4 equations over here. 1 minus x is equals to qg by q, x equals to wf by w, 1 minus x equals to wf by w, and x equals to 1 minus ig by ifg. So, which one is the correct one? Answer is this one is not correct, other 3 are correct. Choose the wrong expression in the third question. So, we are having 4 expressions over here. UF is equals to g into 1 minus x by 1 minus alpha into rho f, UF is equals to gx by alpha rho g, UF equals to wf by rho f af, and UF is equals to alpha into w by rho f af. So, which one are wrong? So, let us see, both B and D, those are wrong. Hope you have liked this lecture. Please join us in the next one. Thank you.